everybody to Practical ML with Oxen AI. This is our Wednesday series spin-off of our Friday archive dives. In archive dives, we go over research papers every Friday, and then in Practical ML, we're implementing this research and seeing how well it works in practice with models that exist out there for us to run on our machines or over API or whatever, however we might interact with them. A quick update on our format. We were a bit ambitious trying to crank out 2 of these videos and vlogs a week. We're a pretty small team and we have a bunch of other exciting things we want to share with you all. So we're going to go back to just the Friday sessions, but we still want to keep this practical ML within the loop. So what we're going to do is we're going to alternate every Friday. We're going to do a research paper, and then the next Friday we're going to do a practical implementation, see how well that research works in the wild, if we can. If it's like a brand new research paper that's hot off the press and there's no code for it, we probably just won't go over that until there is code, because we like to see how these things actually work in practice, not in theory. So for the sake of higher quality content, my own sanity, and honestly a little bit of your own sanity, we'll be moving back to just once a week on Fridays. Part of the reason we do this is to slow down and understand the research, and I feel like we kind of hit the brake or hit the pedal and sped up when that is not the point of these things. So Fridays it is, and with all that being said, we're going to dive into the final part of our RAG series, Retrieval Augmented Generation. This has turned into a few parts, a few separate practical dives. My background is in question answering. I used to work for a startup called Alchemy API, eventually got acquired into IBM Watson, so I worked a bunch on the question answering in Watson, so that's why some of this is near and dear to my heart, and I get carried away with examples sometimes, and I think RAG, it just slots perfectly into there. But a few weeks ago, we looked at Mamba for answering questions given a little context. Mamba didn't work very well at all, if you remember. You can refer back to the blogs there if you're curious or missed it. Then last week, we looked at the retrieval half of RAG using general text embeddings to retrieve the context. So I'll start there as just a little refresher of what we did and where we're going. So I will toss this in the chat for you guys if you want to follow along or didn't catch last week. But the high-level concept is we're going to be building a fact-based question answering system where the user can put in a question, we can go retrieve some documents that may have the answer within them or may not, and then we'll use an LLM to generate the answer. So at a high level, this architecture is pretty plug and play with a lot of elements, and if you remember from last week, this is kind of like a RAG-like system, not full RAG, because we've separated the encoder LLM from the generator LLM. So last week we focused a lot on the encoder LLM, how to compute text embeddings, how to put them into a vector database and search them. And this week we'll be focusing more on the generator half, looking at using Mistral 7B, looking at using Llama 2, and I just threw some OpenAI GPT-3.5 and GPT-4 in there for fun, since those seem to work really well for a lot of use cases. So this is where we'll be focusing today. I decided to switch to a Jupyter notebook for this this portion of the dives because Notion felt a little disjoint going back and forth between the notes and the actual code. So I have hopes that this Jupyter notebook setup will be a little easier to follow. So we have a lot of experiments to go over today and a lot of hyperparameters that we'll be looking at. Last week, we had a document set of 20K documents that was from the squad training set. We're going to bump that up to 100K today. I tried to index over 1 million last night, and I think we're at like 800,000 right now. I was hoping we could do RAG with 1 million documents, but I might just have to add that on after due to lack of time to just index all of that stuff. But it'd be pretty cool to see how this works with 100K documents anyways. For the tool chain, we'll be using OpenAI for raw data storage and data debugging. We have Chroma for our vector DB and embedding search. We'll be using Hugging Face transformers for a lot of these models, the GTE embeddings, Mistral 7B and Llama 7B. And then we'll just be using OpenAI API for GPT-3.5. So the first step for any of this, I have all of this data accessible in Oxen. If you're not familiar with Oxen, you can think of it as a GitHub for machine learning data. I'll be working on this repository. It has about 6 gigs of data in it. All of my experiments are saved off in this experiments directory, and then raw data is saved off in a training data set, just kind of like noisy text data set, and then a development data set. And what these things look like is you have a bunch of questions in here and answers, and then we have a bunch of contexts in here with question IDs. So the reason we have this split up is because we have 8 questions in the question data set with these IDs that all ask about this specific paragraph of context. So there might be questions about who were the Normans and what century did they live in. There's 8 questions like that that we'll be evaluating how well we can retrieve this needle in a haystack out of 100,000 documents, and then once we retrieve it, can we extract the actual answer from it. So there's a Python library that you can download all of this data from. Oxen lets you download just like individual slices of the data, so you don't have to download all 6 gigabytes to get started. And then it also has version control built in, so we can kind of look at different versions of the data as we go along. But the first thing we're going to be grabbing is this embeddings file. So if we go back to our data set, development, I went ahead and computed all of the embeddings for this context, for these contexts. So here's our Normans doc again with the question IDs, but this additional field of the actual GTE embeddings themselves. So it's a 1024 length embedding, and we have one of those for each one of these documents. In the development set, there's only about 1,000 documents that we'll be starting with, which honestly makes the retrieval half pretty easy, and we'll kind of show you how to extend that as we go along. So I should also mention that all the code for this is on our GitHub, and I'll put that link in here as well. It's just under RagDive. I have a little bit of cleanup to do, but all of these scripts are in here, as well as the Jupyter Notebook, so you can follow along. So the first one we're doing is just indexing the data into Chroma. You can give it any of the embeddings files that we have in this data set. In this case, we indexed 1,203 of them, so it's relatively fast. It took like 4 seconds to put all 1,000 of these in. I noticed Chroma starts to slow down after you get over like a couple 100,000. So like I said, I thought I was on pace for 1 million today, and when I woke up, we were only at a couple 100,000. Maybe by the end of the day today, we'll have 1 million documents in there. But this talk is going to progressively go through fetching 1,000 documents, fetching 10,000 documents, fetching 100,000 documents, and then eventually I want to do 1 million. And so if you remember from last week, search is kind of half the battle of RAG. So the first question we often want to answer is, what is the recall of our vector database of our text embeddings in general? And so I have a Python script in there called compute recall. You can give it the number of documents you want to retrieve, as well as that is not a variable that you pass in here. You can just give it n, the number of documents you want to retrieve. And I've pre-computed all of this data so that we can look at it as we go along. But for example, if we ran that script and gave it a recall of 10, basically what would happen is for each question in our data set, we will retrieve 10 documents that could potentially answer that question. You can see they're pretty long documents in general. And then we say what document we found the answer in, how long it took to compute the question embedding, how long it took to find the answer, and then the total time for the query. And in this case, we did find the answer. So if we look back at this question, how long did, there's no way I can pronounce this person's name, work for this Swedish company before she was dismissed? The correct answer was 10 years, and we can see that it's hidden in this third document here. And so the second half of our system is going to have to extract that from all of this context. But you can see, even as like a human looking at these giant text blocks, it would probably take me minutes to sift through and try to answer this question, just from the 10 things that were retrieved. So I did that for all of the questions, all 1,000 questions in our evaluation set. Yeah, Ben says a human without Command F. Assuming that I know the answer, then we can totally Command F it. So I just had a few functions here to compute the recall and plot the recall for this experiment. I ran this on the 1,000 documents that we'd indexed, and our recall was pretty high. And Daniel asks, what's the method for checking if an answer is correct? In this case, since we have the question IDs, and we've linked the question IDs to the context, we can actually do a direct match on the IDs to compute recall. So that's nice. We don't have to do pure string matching in this case. Later on, we will do pure string matching, but for the recall half, it is purely based on the question ID. And then Alex asked, does anyone have a tier list for vector DBs? Chroma, Pinecone, Milvus, Weaviate, etc. I would love this list as well. Like I said, Chroma started to crap out after like 300,000 documents being indexed in terms of insertion speed. So I'm still not even at 1 million, and that's not a huge data set if you think of like web scale. 300,000 documents is nothing. So, assuming we're only looking through the set of 1,000 documents, obviously our recall is going to be pretty high. We're trying to find a document 1 out of 1,000. If we think of that as like a needle in a haystack, our haystack is pretty small at this point. And we were looking at the top 10 documents retrieved. So actually, if you plot this over, did we find the right answer at the first document? Did we find it at the second document? Did we find it at the third, etc.? You kind of get this nice curve of around 10 documents, starts to flatten out. But again, we're only looking at 1,000 documents here. Relatively easy to find a needle in this haystack. So what I did was I grabbed 10,000 random sentences from the pile dataset, which is just like a general random crawl, and I indexed those into Chroma as well. So if we look at this haystack, I thought it'd be fun just to visualize how many documents we're looking at. We have a slightly bigger one. This guy's having a slightly harder time finding the documents. But at the end of the day, we still got 83% recall for those 10,000 examples. So still relatively high, but it kind of flattens out here. And so this means 17 or 16.5% of the time we have no chance of answering the question given the context. We're either going to have to extract it directly from the model parameters or increase our search radius. And then finally, I was like, okay, let's do it for 100K documents. That's a little more realistic for a real world scenario, but still nothing close to web scale. This is our guy with 100,000 pieces of hay looking for his needle. And recall dropped significantly here to 52% recall at 10 with 100K documents, which I thought was a bit suspicious. So I plotted everything, looked at this, and I was like, I just want to double check my work here because that seems like a pretty high drop. And if this is the case, honestly, we probably shouldn't even be trying to answer questions if we have 52% recall and even finding the answers. So I looked at this result set a little bit and noticed something funky, that I was getting a bunch of empty strings returned at the top of my result set, which is not great. I didn't do any data cleaning of the pile before I did this, and it turns out for a lot of these questions, for whatever reason, just a blank document has the closest vector score to these questions. Don't ask me why, but with these GTE embeddings, that was the case, and so that extremely biased my result set here. So what I did was I made sure to clean out all of those empty documents and ran the experiment again. This time, with 100K documents, we're about 74% recall, which is better, but we could still do, I would love it to be like in the 90s for us to move forward. So the next obvious thing you can do is just like increase the number of documents that get returned. In this case, I bumped it to let's return 100 documents for each one of these queries. And now with 100K documents, returning 100 at a time, we're back to that like 92% number. And you can see there's a similar curve of around 20, 40, 60. It starts to flatten out for how many answers we're finding within there. So that felt pretty good, bumping everything up to 100K documents and increasing the search radius to 100, as well as cleaning the data set before we put it in. So this means we can find the answers 92% of the time, but now it's all about once we found the answer, can we extract it from the context? So I have this compute precision script that y'all can run in the GitHub repo. I made it work for a variety of models, and honestly, as these libraries are progressing, a lot of the models are starting to coalesce on a very similar interface, which is pretty nice. I still have a little bit of cleaning up to do in this script, but if we look, this is the prompt that I'm using, and I have a few different functions to run the models. I was playing with Together AI, I was playing with OpenAI, and it's funny because a lot of these clients are starting to use just OpenAI's interface for it, so I could definitely clean up this code. I was just kind of hacking it together last night, but pretty much everybody is using this similar messages array where you have a user or a role, which could be system, user, or GPT, and then some content that you want to put in there. And even libraries like Llama CPP that you can run these things locally is also coalescing around that interface, which I find really nice and makes it easy to benchmark between a lot of these things, assuming my code's a little drier than it is in this example. But anyways, I thought it would be fun to run the precision half of this stuff on OpenAI, on Mistral 7B Instruct, Llama 7B Instruct, and just see how all of these things compare to each other. And in general, I think it would be awesome if we had a little more insight into the result set rather than just plotting numbers. I will plot numbers, but I'm also linking to the full result set in Oxen here, and you can see the question, the context that was returned, the answer, the model's guess, and then whether it was correct or whether even the search found the answer. In this case, the model did a great job of, this was the question, this was the context, and it guessed not in context because it read this context and it didn't say anything about Miss K before she was dismissed. But I did this for all of the question, answer, context pairs in our data set. And in this case, I did a little substring matching as well, so that it wasn't just like raw string matching, because I figure if you're able to return the document from the set of 100,000 and get a percentage of a string match, it's probably the right answer. But again, if the correct answer was just A, like the letter A, then that's going to be a substring of pretty much any word that, or a good portion of the words that are guessed. So it's not perfect, but we kind of talked about last time how it is hard to evaluate these models without explicitly looking at them. So I linked to all the results here, and in general, GPT 3.5 Turbo is the best one that I found for the extraction half so far. But I did do some interesting experiments between what does it look like if we just return one document, what does it look like if we return 3 documents, what does it look like if we return 5 documents. I'll put this more in a tabular format so it's easier to see. But you can see the precision goes down as the recall goes up in general. This is a pretty common curve that you'll see in machine learning. But if you think about it, if we return 5 documents and ask GPT 3.5 to extract the answer from those 5 documents, it has 5 more times the information, so gets it correct less of the time. But if it only has 1 document to look at, it gets it correct a higher percentage of the time, but we're not guaranteed that the answer's in that document. So these are kind of like the things that we're balancing as we go along. Comparatively, Mistral 7B Instruct got about 64%. I thought this was interesting because, okay, let's look at the recall at 1. Mistral 7B, a lot of that paper was talking about how it beats Llama on a bunch of benchmarks and how it's a little more efficient than Llama. On this particular task, Llama 7B still beat it. So again, I think this is just like case in point, depending on your task, run it on an actual data set and don't just take the paper's word for it. And finally, the context length was honestly the biggest blocker for a lot of this research. You'll see that a lot of these result sets are at recall 1 or recall 3 or recall 5, meaning we're only returning 1, 3, or 5 documents. And that is because just the context window of shoving all of that data, if we look at here, like here's the question, we shove all of this in the context, and then we try to extract the answer. I was just running into one, OpenAI's context length limit over the API. They were rejecting if I had too many tokens. And 2, I would run out of GPU memory if I tried it locally. Um, so obviously one thing you could do to get around that is just analyze one of the pieces of context at a time, maybe like one or two sentences at a time, but that also just increases the cost for each query, and isn't that scalable. So I'd say my biggest thing is that context length really matters for RAG. In these examples, would it be correct to interpret the 3-shot as 3 example correct answer pairs provided before the question? And yes, that is correct. So I had this n-shot prompting function, or function to construct a prompt, and I just pass in an n. And so if it was 0-shot, I just gave it, or sorry, if it was 1-shot, I just gave it this example. If it was 3-shot, I gave it these 3 examples. 5-shot, all 5 here. 0-shot, I just cleared that prompt, the n-shot prompting. And then the actual prompt beyond that is just like context, question, answer. So
Did you because I see that like the second and the fifth are the kind of not in context prompt that's sort of teaching it to understand how to not make false claims. Were you like randomizing those 5 when you're feeding them in for the end shot, or was it like when it's 1-shot you just get the top one, like the first one in that array, and you don't see any of the not in context examples?
In this case, I did just have it be in order. I didn't randomize
Cool.
or anything. But what was interesting, let's look at I guess both of these were 0-shot. I realized that this was maybe 30 minutes before the call. I realized that the size of the prompt in general, when you add the end shot, was just slowing down my evaluation a ton as well as just making the context even bigger. Like, now I don't know exactly how many tokens this was, but that was part of the reason that I couldn't even evaluate the RAG, is because half of the context window is just our end shot prompting, and then half of the context window is the RAG. And when you're looking at like a couple thousand tokens being able to fit in there, that fills up really quickly. So I started these 0-shot experiments like maybe 30 minutes before the call, and saw that they were getting like pretty competitive with the end shot. But I would love to continue like break this down so it's a little easier to follow. But that is, yeah, it's kind of recalls how many documents in the context window, and then end shot is how many examples we gave it beforehand. Cool. So this whole pipeline, I think, is getting close to being pretty plug-in playable in that GitHub repo. I have a few things to clean up the code, but it's kind of just these 4 steps, and you can compute precision and recall on your data itself. So I have computing the embeddings, given a context file. Right now it accepts a Parquet file, but I want to just make it generic for any sort of tabular data, and make it generic for which columns you're indexing. And then you can index all of those embeddings once they're computed into Chroma. Again, this is like relatively quick if you have a small data set. I think there could be something interesting about having even separate Chroma or vector DBs for different types of information. Like maybe you have your factual information in a small database over here that you're looking up. Maybe you have questions in a small database that you're looking over here, but honestly one large database wasn't working great for me just in terms of raw indexing speed right now. Then you can compute the recall, given a number of documents that you want to return. This L is just a limit on the first 10,000 in your data set. You give it a questions data set, you give it a Chroma database, and then you give it an output file just to write all those results to. And then you can compute precision given this results file. So kind of just breaking it into these 3 steps so that one half of your team could optimize on the search, another half of your team could optimize on the extracting answers, and you could kind of come together for a system that works really well end to end. I did a bunch of these experiments, and honestly, I have a few more that I just haven't uploaded yet because I was doing it right before this call, but I would love to even just like get a little RAG leaderboard together, and as long as we kind of have all of our results in the same format, we could not only just look at the numbers, but we could dive into the actual result set here, find all the ones that we just didn't even find in the search, or find the ones that we found in the search but didn't find a correct answer for. So a cool feature that we're kind of working on is natural language queries for here. So you could say something like, find me all the rows where we found the answer and is correct, is false. And this will just translate it to SQL for you, run it on the data set, and now we have a sub data set of all the ones where the answer was somewhere in the context, we just didn't extract it. So you can kind of debug from there, and here's a great example of us guessing not an exact string match here. Let's look at another example. Who was Boleslas II of Masovia? I guess the right answer was Prince of Block, and the model said they are Boleslas II of Masovia, which is pretty hilarious because I guess they're not wrong. But it is fun to, like, when people report their accuracy numbers, let's look at like what the actual responses are, because a lot of the time these first 3 that I looked at, I was like, okay, this just is a string match problem here, right? Or one of them technically was right, but here's another string match problem. So honestly, now that I'm diving into this live with you guys, a lot of these might actually be correct. We were just marking them as false in here. So pretty cool to walk through like that. And honestly, coming from my times at IBM Watson, the fact that I could spend like a couple days just computing embeddings, creating a vector database, and stringing up an LLM on top of it, and it's only a couple hundred lines of code to build a system that's honestly pretty competitive with what IBM Watson was back in the day, just kind of blows my mind. And there's so many different models and different both embedding models, vector databases, and generation LLMs kind of in this pipeline, that I feel like it's almost just like putting the pieces of the puzzle together and figuring out which one does the best search, which one does the best generation, which document index fits my data profile, and you can start to build pretty robust QA systems with not a lot of pieces, which is pretty awesome. Yeah, so Daniel said, it's just like me on any test question. I didn't know the answer, but just had to write something down. Exactly. Yeah, these LLMs are more like us than maybe we'd like to admit. I feel like it's more like answering 2, but the real answer is 2.0. Yeah, totally. I think, part of this is a few ways that we could solve it is just having more sets of answers that we accept, or a lot of people are starting to do like GPT-4 just compares these 2 without any of the other context, and we're like, do these 2 strings say the same thing or not? But that is a little of a slippery slope, in my opinion. Any other high level thoughts on this stuff? I tried to break it down into just 4 steps anybody could run and just the types of things I like to look for in terms of precision recall. And now that we're diving into the actual data, like maybe your matching algorithm at the end. Um, but I hope that's helpful. Evan said, I think I mentioned something like clip, but for a question and potential answers. You said that there was something like that. Yeah, it's funny because that is how the GTE model was trained. So this is the model that we were using to compute our text embeddings. And this is, they use something called multi-stage contrastive learning. So they're actually trying to embed these sentences into the same space, but they could be like a question document and a document that has the answer that aren't necessarily the same content, but you'd want to retrieve in the pair. So GTE does do that contrastive learning. This would be a fun paper to do on Friday, on one of these Fridays, actually, because I think it's pretty cool. Sounds pretty cool. Daniel asks, in your experience working on QA in the past, how much difference does RAG make in a QA compared to other tools? I'd be curious what you mean by other tools. When we worked on Watson, we just did a pure TF-IDF search of the entire document database, and we didn't do RAG at all, and that honestly gives you pretty high recall in general. So I think there are tools built into Elasticsearch or any of these other search engines that you could use to replace the first half of it. And then I think it would also be interesting in these benchmarks to remove the RAG step and just return the answer from the model's parameters and see what the accuracy is. But Daniel, did you have any other tools you were thinking of when you asked that question? While we let him type. Oh, yes, you can call in if you'd like. That would be great. We're still getting used to this platform, so it'll be a fun experiment.
Yeah, there should be a phone, like a green phone button, on your dashboard there.
Mm.
Hello? Is that working? Okay, nice.
Yeah. Hey, Daniel.
Hey, hey. Yeah, thanks for answering the question. What I'm curious about is I didn't want to say, before RAG because I think something like semantic search has existed for some time, but LLMs were not maybe quite at the level they are in the recent year and a half ish.
Yeah.
But just in general, I'm just very curious about how much of a difference does this LLM plus RAG combination actually make compared to really what was the state of the art? I'm not sure if that's the state of the art now, but what would be considered the best option prior to this whole LLM plus RAG combination? Part of it is just because I'm curious whether, does it make a substantial difference? Is it, really this has been like a tremendous jump or, things that were before. I don't really have any specific things in mind, but anything that came
Yeah.
before was still really good and just like an incremental improvement.
So my intuition on that, and I kind of, so to be honest, I took a break from NLP from like 2017 to 2021, where I worked on more computer vision stuff. So I kind of have a blind spot in that space. But in general, I would say that this RAG architecture has just simplified things a lot. And there were state of the art techniques that had a lot of feature engineering or had like a bunch of different components in there that said, okay, let's break down the question into subject, verb, object. Let's break down every document into the parts of speech. Let's do some like crazy NLP matching algorithms, kind of like all the feature engineering that you used to do in computer vision before AlexNet came out. And those systems, honestly, like IBM Watson itself was one of those systems. I feel like if you gave it this exact task, they would blow it out of the water. Like 73% accuracy is not really state of the art on the squad data set. I think they even have a leaderboard here, and I believe that it's in the 90s or so. So yeah, like top F1, which is precision and recall, kind of like average, is in the 90s.
Okay.
So I would say RAG in general just simplifies that pipeline and makes it so you don't have to write as much code to even get up to like an 80%, but there is a ton of feature engineering and tricks that you can kind of do at the going from 80 to 90, 95 to 98 or whatever.
Okay. All right. Yep, thank you. That's very interesting. Thanks.
Yeah, totally.
How do I leave this? Do I just leave? Do I just click leave?
I think so.
All right.
Yeah, we'll see.
Give it a shot.
Great to have you on. And then Alex in the chat asked, so the precision recall here is whether the LLM found the answer in the relative context per the embedding search. Yes, so recall is whether it found the answer, and precision is assuming it found the answer, did you extract it from the context? Let's see. Previous state of the art was BM25 on keyword search. I haven't heard of that, but maybe we can do a live search for it. And if anybody else wants to look at this, Bert QA BM25, nice. That sounds like a lethal combo just from the name. Cool. We'll add this to our candidate papers if anybody wants to look deeper into it in our Discord. Well, awesome. That was a fun one. I had fun going over it, just given my background. We're going to switch to multimodal and look at Llama, which we did the archive dive for last week, I guess. Time is just flying by. And so we're going to look at how to fine-tune Llama and just like use it on some actual data in the wild and see how well it works in the next practical dive. The next archive dive itself, we're going to be looking at switch transformers, which is a paper that inspired a lot of the work on Mixture of Experts, or MO, if you've seen that. And in the past couple weeks, we've seen like Mistral come out which is a mixture of a bunch of the Mistral models, and somebody yesterday I saw made a Mamba Mo, a Mo Mamba, a Mo Bamba if you search for it on Google. So a lot of people are playing with this technique of how do you combine knowledge from multiple LLMs in a network. I haven't read the paper yet, so that's about as far as I know so far. So we'll be going over that Friday. And then the week after that, we have we have a guest presenter, Daniel, and he'll be doing attention sinks. So that'll be a fun one as well. Hey, Evan.
Am I mute? Okay.
There.
Can you guys hear me?
Yeah.
Yeah, I feel like it's interesting that really what we're doing is we're creating like a distance, like a similar, like a learned distance.
Mm-hmm.
I guess I don't understand how it's possible to learn like a general representation of the information. Like it just like it fundamentally seems impossible based on like one of the examples we gave with like man and woman. Like in some contexts, those should have a short distance, but in others they should be very large.
Yes.
but you won't
Yes.
know until you actually ask the question. So it just seems, how did they, are you saying that they came up with a solution to that specific part?
That's a great question. And I think an awesome example of this is like we had a customer that was working in the medical field, and like text embeddings, like general text embeddings and medical text embeddings are very different, because the things you'd want to distinguish between, like for a general text embedding, everything in the medical space is pretty close together.
Yeah.
But in the medical space, like you might want to very much distinguish between this disease and that disease.
Okay.
They
So
might
switching
have a lot
between
of
different embedding contexts?
Yeah, so different domains is a problem that people have all the time, and I think it is hard to have one embedding to rule them all.
Yeah.
But
It feels like something like Clip. I don't know if that's what this paper is. I mean, I haven't read it. It'd be really interesting to see if we do end up doing like a Friday thing on it.
yeah,
But
totally.
it just seems like fundamentally, like there's no way you could compute this distance ahead of time.
Yeah, or you might need, like you said, like maybe once you get the question, maybe you have another layer on top of it that can like do another transform to understand the context of this question better.
Yeah, like maybe there's like some sort of like general embedding space, but then like given the question and the embedding, the like the embeddings, like you said, like a transform based on the context.
Yeah, that would be really cool.
Yeah,
Because
I'll
a
have
lot
to
of
look
this
at
RAG stuff, yeah, a lot of this RAG stuff does work in the text space, and then they just like drop the embeddings and leave them to the side.
I'm curious, has anyone, I kind of thought about this problem like when it started getting popular, like back in March, and I never ended up moving on it. I'm wondering if anyone else had heard of someone doing like something like this, which is like, given a piece of information, generate every question that would be the answer to. So like say like, okay, here's the answer to the question, like George Washington was the first president, like almost like Jeopardy.
I was just gonna say Jeopardy GPT.
Yeah. And then what you do is you actually create the embedding on all of the questions, because you're essentially measuring the distance between the question and the answer, which is impossible. But like, what if you were comparing question to question? So I don't know if anyone's done, like, I assume someone has done that already, but I'm just wondering if you know of the example.
I don't off the top of my head, but I love that idea of like, one, I think there is a bunch of synthetic data approaches that we could start to leverage existing LLMs to just generate a bunch of these.
Yeah.
I still think there
So it
might
seems
have to
like-
be
yeah.
some, yeah.
There was also another thing that I saw. I have no idea where I saw this, but it was like they would pre-process all of the chunks of text that they were going to embed. So like it would kind of remove pronouns. So it would make them more atomic units of information. So like, I feel like if you had a giant chunk of text, you split it up into tiny chunks. You made sure each chunk had enough context to explain itself by substituting out the pronouns and everything. And then you generated a list of 10 questions that piece of text would be the answer to. And then you had 10 keys pointing to the same value, or 10 embeddings, 10 different embeddings that were different questions that have been embedded to that. Then you're comparing apples to apples instead of questions to answers.
Totally. I think I'm following, but I would love, this is like
It
starting
would be
to get
really
to
easy
it.
to try too, which is why I'm surprised there isn't like a well-known example. So I'm wondering if it just doesn't work like that, or if it's just one of those obvious things people haven't tried yet.
Yeah, maybe if anybody watching this just joins our Discord, and if they find any examples, let us know. I also want to point out, when I was doing some of the random noise in here, there is just like, what I did was I took the red pajama data set and sentence split it just with like a generic sentence splitter, and took a 2-sentence window. In this case, I guess these might have been line delimited beforehand, but there is just like a lot of junk in this data set. Like this was a 2-sentence window according to our sentence splitter. And so if we're trying to do like a factual QA, and this is the type of stuff that's in your RAG database, like this isn't going to answer any question. This was not the best way to split it up and put it into our document database. So I think there is something around just like the quality of stuff you're searching over.
I feel like maybe the reason it hasn't been done is it's been prohibitively expensive to clean a data set like this. But
Yeah.
now that there are local models that can be fairly straightforward, fine-tuned off of something like GPT-4, like if you got GPT-4 to do this for like 100 examples, or maybe 1,000, it would be relatively cheap, but then you could distill a smaller model to do the same thing,
Yeah.
potentially. That's local and maybe like 3 billion parameters, potentially even.
I love that idea. I feel like this is going to be the year of the small LLMs. Like the amount of work that people are doing to run these things on MacBook Pros or limited resource. Like I feel like we're going to have some pretty insane results by the end of 2024.
I mean,
That's gonna be my
it
guess.
feels like there's so much low-hanging fruit just because things are expensive, and like as the cost comes down, it's going to be more crazy than I think any of us imagine.
Totally agree. Cool. Thanks for hopping on. Evan, sounds like an integration between LLMs and a knowledge graph, maybe.
I have
Do you have any
never
experience
worked with
with
knowledge
knowledge graphs?
graphs, so I actually don't know what you're talking about.
Yeah, maybe. I feel like I hear people talk about knowledge graphs all the time, and everybody has a different definition of them. But maybe we can do like, if anybody knows like some.
I can kind
Good.
of like intuit what I think that means, which is I think that like you have some noun and you see how that like relates through some transition to everything else in the graph. Like I don't know what that connection would be, but I can kind of think about it.
I mean, part of it could be like, so if you think of a knowledge graph, how do you traverse from one node to another? I wonder if there's something with
Honestly,
LLMs.
I think
to
maybe
compute the embedding space.
what you're getting at potentially is like an LLM constructing a knowledge graph. So like the knowledge graph has been like historically really expensive to compute because it had to be done by hand, but now we can like do it in a much more low resource way.
He also found an archive paper unifying large language models and knowledge graphs, a roadmap. I'll toss this in our Discord too. Sweet. All right. Well, we're running up on the hour here. Thanks everybody for joining live. The Oxen team is going to jam on some product stuff after this. So excited to see you guys there. And thanks everybody who joined live. We'll see you again on Friday for this stuff. And thanks for hopping on as always, Evan.